And I should say right off the bat that this is all joint work with Jacob Tsimerman. So just to start, for k, a number field, and for an elliptic curve over k, we're going to be interested in the p-torsion group scheme of E, which we'll, for the purposes of this talk, think of as being encoded by the p-torsion Galois representation. And of course, it's an easy fact that if E is Cm, then this representation is not surjective, simply because as soon as the extra endomorphisms of E are defined, this representation is abelian. On the other hand, it's a famous theorem of Serre that if E is not Cm, then it's essentially always surjective. Then this representation is in fact surjective for P sufficiently large. And this theorem in hand, it's natural to formulate the conjecture, which Serre did, that the prime that you have to go up to in order to get the surjectivity can be taken uniformly in the elliptic curve E. Okay, so the conjecture is that for k fixed, then there exists some number nk such that this surjectivity is achieved for all non-Cm elliptic curves over k, assuming p is bigger than this constant nk. Okay, so this is called Serre's uniformity conjecture, by the way. Let me make a few observations about this conjecture. This talk will not really be about this conjecture, but since I've stated it, let me at least tell you a little bit about it. So if we, in particular, take k to be the rationals, then it's expected / hoped that this constant is 37. Perhaps the most compelling reason for which is that by Mazur's isogeny theorem, at the very least, we know that the image of this representation for all elliptic curves is not contained in a Borel. Oops. For p bigger than 37. And this is sort of a third of the work, in a sense, because if this representation is not surjective, it must lie in a maximal subgroup, and those are classified. The maximal subgroups look like they're either Borels or they're normalizers of Cartans, or there's a couple exceptional things it could be. And again, by Mazur's theorem, this doesn't happen for p bigger than 37. Serre showed that this doesn't happen for p bigger than 13. And sort of this is the only open case. In fact, within this case, recently it's been shown by Bilou and Parent in the case of the normalizer of a split Cartan. So the only open case is. Sorry? Oh. And one more thing I'll say is that by work of Merrill, there's a uniform bound on the torsion of elliptic curves over a number field K. So there's a bound on torsion, the order of torsion of elliptic curves over K that only depends on the degree of K. So you might hope that in this conjecture, this bound nk can be chosen to only depend on K through its degree. Okay, so like I said, this is not a talk on Sayre's uniformity conjecture. What we'll actually be interested in is a conjecture inspired by the philosophy behind this conjecture. So let me make the following vague generalization in an attempt to explain this philosophy. And the idea is, if I now look at abelian varieties parametrized by some fixed Shimura variety, so A over some number field K, some principally polarized abelian variety, parametrized by some Shimura variety X, then the point is we should expect that the p-torsion representation will be as big as possible unless it has a reason not to be. So should be as big as possible. Okay, so what do I mean perhaps slightly more rigorously? Well, I mean that, so for instance, it should be surjective onto some fixed algebraic subgroup of GL2 GkFp uniformly in the abelian variety A. So for P sufficiently large, independent of A, so long as A doesn't have a reason for this not to be surjective. In other words, so long as A doesn't lie on some Shimura subvariety. Shimura subvariety. Okay, so this is extremely vague. Let me at least spell it out in one other context, which is what we'll care about. So let's, for instance, look at abelian varieties parametrized by the square of the modular curve. So in other words, let's look at pairs of elliptic curves. And for any pair of elliptic curves over K, with this conjecture says that, or this philosophy says that the p-torsion representation should be surjective for P sufficiently large, again, independent of E and E prime. So long as E and E prime, the pair, doesn't lie on a Shimura subvariety of this product, that is, unless either E or E prime is Cm, for which it clearly fails, or if E is isogenoous to E prime, for which it also clearly fails, because then the image will always land in the graph of the isomorphism. So note that, let me call this star, if it is the case that the product of the p-torsion representations of E and E prime is surjective, then in particular, that means that the two p-torsion representations can't be isomorphic. So with this simple observation, this brings us naturally to the following conjecture, which was first formulated by Frey and Mazur, which says that for K, a fixed number field, there exists some constant nk such that Well, such that an elliptic curve is determined by its p-torsion representation up to isogeny. So if I look at the set of all elliptic curves over K up to isogeny, and I look at the map into in mod P Galois representations given by taking the p-torsion representation, then this should be surjective. This should be injective, as long as P is bigger than nk. And I should add that part of the conjecture is that, again, optimistically, we expect that for K, the rationals, this constant should be 13, just because that's the smallest thing it could possibly be. So given this natural sub-question of Serre's conjecture, we can ask the same thing for the Frey-Mazur conjecture. Can we take this constant to only depend on the degree of K? So we can ask if this can be done uniformly in the degree of the number field. And second, we could also ask, well, what about for function fields? In which case, what would it mean? What is the analog of asking it to be uniform in the degree of the number field? Well, the analog is for it to be uniform in the gonality of the curve C. Recall that gonality is the minimum degree map to P1. Well, finite map to P1. Okay, so the theorem I want to describe today is a geometric version of this last statement. So the theorem is, so now take K to be an algebraically closed field of characteristic 0. Then for any B, which is going to be our gonality bound, there exists some NB such that for any complex curve whose gonality is bounded by B, it'll be the case that an elliptic curve over the function field of C is determined by its Galois representation. So in other words, if I look at non-isotrivial elliptic curves over the function field, again up to isogeny, because the p-torsion representation will never distinguish between isogenies, that this injects into Galois representations where this map is again taking the p-torsion representation for P bigger than NB. Okay, so it's a direct analog of this Frey-Mazur conjecture. It's effective in a theoretical sense. That's right. It's effective in a theoretical / lazy sense. We could have a number, but we don't. Okay, so let me say a couple things about this theorem. So first, well, by Riemann-Roch, the gonality is always bounded by the genus. The gonality of C is at most, in fact, strictly less than the gonality than the genus of C. And in fact, you can do better than this. But the point is that if we if we have this result uniformly in the gonality, it implies the weaker result uniformly in the genus. So as a corollary, we have the same theorem, but uniformly in the genus. And the second thing I want to say is that we can also prove this theorem where now we're not concerned with elliptic curves over the function field of C, but we're concerned with fake elliptic curves. So this is also true for fake elliptic curves. And by that I mean principally polarized abelian varieties that are naturally parametrized by a Shimura curve. By a Shimura curve. So I mean this theorem is really a statement about one-dimensional Shimura varieties. It's not. It's very much a consequence of the geometry of the Shimura curves and the modular curve, although the modular curve case is substantially more difficult because of the cusps. So I mean, just as an example, for instance, you could look at abelian surfaces with multiplication by an order in an indefinite quaternion algebra over Q. Order in blah, 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 blah. This is just an example of a possible moduli problem that is parametrized by a Shimura curve. Okay, so as it's a statement about one-dimensional Shimura varieties, it's not surprising that the proof is very geometric. So let me briefly describe, before describing the proof, how we encode this in the geometry of a particular modular surface. So given the coarse compactified modular curve, we, as usual, let xp be the curve with full level structure. So this parameterizes elliptic curves together with some full rigidification of its p-torsion group scheme. And of course, this is a Galois cover of x1 with Galois group PSL2 FP. Let me call it Z mod P. Okay, so it's not hard to build a surface parametrizing pairs of elliptic curves whose representations are isomorphic. In other words, a surface parametrizing counterexamples to the Frey-Mazur statement. Namely, we take a product of xp with itself. This, of course, parametrizes elliptic curves, each of whose p-torsion has been rigidified, sort of independently. But of course, if I'm given these isomorphisms, I'm in particular given an isomorphism between them. And now if I mod out by the diagonal action on PSL2 ZP, it'll precisely mod out by choices of this common trivialization while preserving the isomorphism between them. So by taking the quotient by the diagonal PSL2, we'll obtain a surface ZP, which is the coarse moduli space of pairs with isomorphic, with a given isomorphism of p-torsion. Okay, so as I mentioned over here, one easy way to build an isomorphism between the p-torsions of two elliptic curves is by giving a isogeny between them of degree prime to p. So lying inside this surface, for any m, we have a curve called the mth Hecke curve, which parametrizes pairs of elliptic curves together with an isomorphism of their p-torsion. Oops. That comes from some cyclic degree m isogeny. Okay? And this is, of course, I mean, there's a natural map from the modular curve representing pairs of elliptic curves with such an isogeny into ZP, and this is just the image of that map. Okay, so in this statement, we have the following theorem. I'll call it theorem prime, which is slightly stronger than this theorem, which says that for B and NB as above, in other words, as in this theorem, then for any curve C that maps into this surface, whose gonality is bounded by B, factors through a Hecke curve. Which will imply the theorem, again, because, I mean, giving a map into this modular surface is the same as giving elliptic curves, two families of elliptic curves over C with a global isomorphism of their p-torsion. And saying that that map factors through a Hecke curve is precisely saying that there is a global isogeny between them. Okay, so these surfaces ZP have been studied previously in connection with the Frey-Mazur conjecture. So let me say that perhaps the first person to really look at these was Hermann, who showed in particular that ZP is of general type for p bigger than 11. And this was in the context of, I mean, it's ZP you can think of as sort of a degenerate Hilbert modular surface, where you look at abelian surfaces with a whose endomorphism algebra includes all 2x2 matrices over the integers. And sort of this is the angle that Hermann was taking. And note that, like I said, I mean, if you can rule out curves with a gonality bound, in particular, you can rule out genus 0 and 1 curves. So for p sufficiently large, the only genus 0 and 1 curves on the surface are the genus in 0, 1 Hecke curves, HM, of which there are only finitely many. And in fact, only HM for m less than or equal to 49 could possibly have genus 0 or 1. And the point is that once I know the surface is general type, then I'm in the realm of the Bombieri-Lang conjecture, which would then imply that there are only finitely many exceptions to the actual Frey-Mazur conjecture for any fixed number field k. So for any k, there are there are finitely many, at most finitely many exceptions to the Frey-Mazur conjecture. Just because k points of this surface ZP are exactly counterexamples to the Frey-Mazur conjecture, and the conjecture is saying I can go up to p large enough such that all k points lie on these Hecke curves HM.
And now you'd be back in the original problem, not the function.
Yeah, that's right. I'm saying the two versions connect, and the overlap is explained by the Bombieri-Lang conjecture, which allows us to go from statements about there existing curves in my surface to statements about.
But I guess what you're saying is even the Bombieri-Lang conjecture doesn't imply the result, it only implies it up to finite.
That's right. That's right. And furthermore, it only apply only with this result does it imply that there are only finitely many exceptions. Because I mean, a priori, you don't know that there aren't some other random genus 0 or 1 curves. Oops. Okay.
By the way, Bombieri himself is quite suspicious.
Well, okay, I'll put it. Okay. So let me spend the rest of the time outlining the proof of this theorem. And so to start with, let me discuss some rather easy reductions. So first of all, if I have, suppose I have some curve in this surface EP, and suppose...
And this is sufficiently explicit that they have now this whole theory of unlikely intersections. I suspect there's a very concrete version there which could apply. I don't know. Did you speak to Jacob about that?
Oh, no, I haven't. No, we haven't discussed that.
Because of these kind of methods of Euler, there are now many theorems of this type that have been proved. But methods not so different to what you're doing. And these general conjectures in these special cases are quite safe.
Oh, yeah, they might have a handle on. Oh, that would be fantastic.
That's the way instead of moving that matrix.
Okay, so suppose I have a curve mapping into the surface, and suppose that this curve has gonality B. So there's a degree B linear system on C.
Now you back up with the complex one.
Yes, now I'm back. Now I'm going back over to this theorem. This is a geometric statement. The base field is C. And for the rest of the talk, it'll always be over C. So suppose I have some curve in my surface, and suppose it has bounded gonality little b, bounded by big B. Well, the point is that this linear system naturally gives a map from P1 into the B symmetric product of this surface. Okay, so right off the bat, I can reduce theorem prime to a statement about rational curves in the symmetric products. So it's enough to rule out rational curves in the capital B symmetric product of ZP. Okay, now suppose I had a rational curve in the beat symmetric product. Well, I mean, ZP itself is a nice quotient of XP cross XP. So the symmetric product is a quotient of the 2B squared of XP. By some group which is an extension of the symmetric group on B letters by B copies of the diagonal PSL2 FP. So if we pull P1 up to some curve C here, the proof will be by analyzing the ramification that this map could possibly have. And the heart of the proof, really what it all comes down to, is showing that the ramification of this map alpha, the degree of the ramification divisor, is little o in the volume of C. In other words, the possible ramification of a map obtained via this construction grows much slower, well, grows slower than the volume of C. Right. So I was just about to say, so I mean, in order to make sense of this volume, I need to give you a metric on this. So the metric I use, I mean, this has a natural uniformized metric coming from the uniformized metric on each of the pieces, so on xp, I put the constant scalar curvature -1 metric. And I put the product metric on this guy. So this has a uniformized metric. And the main thing I'll be using about this uniformized metric is, I mean, on each curve, and this is a Kähler-Einstein metric on each curve, and the pullback will have the property that if k is the canonical divisor, then if I normalize correctly, then the canonical degree of a curve will just compute the volume for me. Okay, so if you don't want to think about volume, just think about the canonical degree, or vice versa. Okay, so in other words, the canonical degree of a curve in this product grows much faster, arising by this construction, grows much faster than the ramification of the map down to P1 could possibly grow. So let's just show how to prove theorem prime, assuming this claim. That's correct, yeah. Assuming that this P1 isn't in one of these heckathings or a diagonal, then this is true. Right, yes. So, I mean, what would be the proof? Well, let's let di be the degree of the ith projection of this curve to xp. Okay, it's the canonical, I mean, this is just a big product of curves. So the canonical degree is just equal to, I mean, the canonical divisor is just the pullback of the canonical divisor from each curve factor. And therefore, it's just equal to this times the sum of all these degrees. Let's call it d. And the point now is that let's look at minus the Euler characteristic of this curve. Well, there's sort of two maps from C at our disposal. On the one hand, I could take one of the projections which has biggest possible degree. In particular, that means its degree must be at least d over, I mean, the total degree d over 2 times big B. So by using ramification, using Riemann-Hurwitz applied to that projection, we know that 2gc minus 2 is at least as big as this. Okay, but of course, I mean, as I just computed for you, that's just the canonical degree of the curve, or if you want to think of it as the volume of the curve. So on the one hand, the Euler characteristic of C gets more and more negative with the volume of C. On the other hand, if I apply Riemann-Hurwitz to this map alpha and only remember the ramification, then I get a bound in the other direction of this form, simply because, you know, the missing term in Riemann-Hurwitz is negative. And therefore, by this claim, if the ramification can't hope to keep up with the volume, then we get a contradiction for p sufficiently large. And that proves the theorem. Okay, so it all reduces to this claim. So how do we prove such a statement? Well, the idea is that, I mean, how can this map alpha achieve ramification? Well, it achieves ramification when C goes through certain special subvarieties of that big product of curves. So alpha ramifies when C passes through special subvarieties. So let me be a little more precise. What do I mean by that? Well, there's sort of two flavors of ramification. C could go through one of the diagonals, in which case it's ramifying because of the SB action. Or on one of these components, it could be going through one of the singular points of the quotient map from xp cross xp to zp. Okay? So the first kind of ramification is when a coordinate is equal to a ramification point of this quotient map. So, I mean, where does this quotient map ramify? It ramifies at points x, y that have a common stabilizer under the PSL2 action, where x, y have a common stabilizer, a common non-trivial stabilizer. Okay, so in particular, x and y both have to have a non-trivial stabilizer, so automatically they have to either be x and y both have to, in moduli, lie over the elliptic curve with j invariant 1728, j invariant 0, or they both have to be a cusp. So x and y both, they're either both the elliptic curve with Cm by Q adjoin I, or that with Cm by Q adjoin omega, or they're both cusps. Okay? And on top of this condition, they must, in addition, have a common stabilizer. So, I mean, remember that x and y are parametrizing not just elliptic curves, but also a full level P structure. So the common stabilizer has to preserve those, also stabilizes the level P structure. Okay? So just terminologically, let's call the points x comma y of this form. This is really poor terminology, but it already existed in the field. We'll call them Cm points, and we'll call these bicusps. Okay? So this is one type of ramification that alpha can have. And the other, like I said, is when C passes through a diagonal. Okay, so the strategy for proving this claim is twofold. We're going to show first that these special subvarieties hyperbolically repel each other. Not only do they hyperbolically repel each other, but they repel each other more and more as p goes to infinity. By which I mean, in the hyperbolic metric, their distances just grow as p goes to infinity. And the second statement is that I can measure the incidence of a curve along one of these special subvarieties in terms of its volume. So the second point is that incidence along a special subvariety costs volume. Okay, and then once I have sort of points 1 and 2, then the proof of this is clear because, I mean, suppose I have a curve that has to get a certain amount of ramification. Well, it has to go through these special subvarieties a certain amount of time. But if these are getting further and further apart, that's going to cost more and more volume as p goes to infinity, which is why the volume grows faster. Okay, so let me say that both of these statements, as I said, this is a statement about one-dimensional Shimura varieties. Sort of both of these are heavily using this context. I mean, property 1 is really a consequence of the fact that the uniformizing groups of this product of curves are arithmetic, and part 2 is really using is very fundamentally using the hyperbolic metric, the fact that I have a uniformized hyperbolic metric on these moduli spaces. Okay, so let me briefly give you the idea behind how to prove 1 and 2. Let me start with 0, though. So just as sort of a baby example of how modular varieties tend to get bigger and bigger hyperbolically as level goes to infinity, let me first discuss the expansion of xp itself. Okay, and precisely what I mean by this is, so recall that the injectivity radius of xp, which is denoted by rho xp, is the largest radius such that around any point there is an embedded hyperbolic disk of that radius. Okay, so for any point x in xp, if I look at the ball of radius r, the hyperbolic ball of radius r, then this is embedded into xp isometrically. Okay, so the picture you should have in mind is that if I look at some fundamental region for xp, and I look at the uniformizing map, say it looks like this, then around any point I should be able to draw a radius r ball that injects under the covering map. So it maps to some embedded hyperbolic disk. So this is the center. Okay? And then, of course, I mean, with this picture, I mean, the injectivity radius is sort of the biggest radius that I can get without this disk coming back in on itself. So equivalently, you can think of this injectivity radius as half the length of the shortest geodesic. Because as soon as this disk wraps around itself, I get a loop, which is length minimizing, therefore must be a geodesic. So if I only go to radius half the length of that loop, then I'm good. Okay? So it was an observation of Mazur and Sarnak that in fact the injectivity radius of xp grows, which is what I mean by the expansion of xp. It's sort of getting uniformly bigger and bigger, more and more stretched out. And so the actual statement is that the injectivity radius goes like 2 log p. Okay, and maybe I'll I'll briefly spell out the proof, because why not? The proof is pretty simple. I mean, so what am I doing? I'm looking at the minimum distance between z and gamma z, where I take the minimum over all z in the upper half plane and all gamma in gamma p, except that I don't want to include the parabolic elements because, I mean, those geodesics are homotopically trivial in the compactification. So I'm only looking at semi-simple guys. And the point is that if I'm only looking at semi-simple guys, since I'm taking a minimum over all z, I may as well assume that gamma is diagonalized. So in other words, that it's a dilation, a, where the square root of a plus 1 over the square root of a is equal to the trace of gamma. And then I'm taking the minimum over all z and gamma. And it's not hard to show that this minimum is achieved for a fixed gamma when z lies along the geodesic preserved by the dilation, in which case the distance between z and az is just log of a. So now we're looking at the minimum of log a over all gamma. And finally, the point is that, a is related to the trace of gamma. Well, in gamma p, the smallest possible trace of a non-trivial element is p squared minus 2. So the trace of gamma is at least roughly p squared, and therefore a is at least roughly p to the fourth. And therefore, the minimum length, the shortest length of a geodesic is 4 log p. Okay, so the trace of gamma is at least p squared minus 2, which implies that this is equal to 4 log p. So the injectivity radius is 2 log p. Okay, the point for us is that it's growing pretty rapidly. Sorry? Because both the off-diagonal guys are divisible by p.
Very useful. Yeah, it's a good question.
Was this before the shoe? The work with shoe? Same idea right there, right?
What we really, the hard part of what Gude and I did was to make it homologically non-trivial. But you don't even need that.
Okay, so now that I have some understanding of why, as level grows, I become hyperbolically more and more spread out, let me briefly talk about one. So let me talk about the repulsion of special points. And let me restrict myself to the case of these CM points that I mentioned. Okay, and so let's refresh our memory what these CM points look like. Well, like I said, they automatically have to have the same J invariant. So we know that they must look like x, gx, for some element g of PSL2, where x is either going to be I or omega, essentially. But more than that, it's not just a point like this, because these guys have to have a common stabilizer. So if t is in the stabilizer of x, then t has to simultaneously stabilize this and this. In particular, that means g commutes with t. Okay, so g is automatically in the ring generated by the identity in t. So as soon as we lift g to an integer matrix, we'll get that this lies on some Hecke curve. But without knowing anything about g, we have no control over sort of what Hecke curve that might lie on. And the form these repulsion results take is that, one way to say it is that if I look at CM points that are far away from the Hecke curves, then the distance between them grows more and more. Or equivalently, as p goes to infinity, the only places where the Hecke curves sort of bunch up is near the CM points. Okay, so the precise proposition is that for any radius bigger than 0, there exists some m such that for sufficiently large primes and any 2 CM points on xp cross xp, and of course I should say that these are CM points of the same type. Okay, they're both sort of, both factors in both of these have the same J invariant. Then, in order for these 2 points to be close together, it must be the case that they lie on a low-degree Hecke divisor. Okay, so not only is it the case that as p goes to infinity, the Hecke divisors only bunch up near these CM points, but they only the low-degree ones sort of bunch up. And this is sort of essential for the proof of our theorem. So in the interest of time, let me just briefly discuss sort of how you prove this. The point is that, so as I said over here, I can assume C looks like x comma gx for some g that commutes with t. And C prime, well, has to vaguely have the same form. Let me write it like this. G. Okay, I mean, I can write it as some group element times x times some other group element times x. I know both entries of C prime have to be translates of x because they're CM points of the same type. But let's write it in this way. And the reason I write it in this way is so that the condition for this to be a CM point comes down to t commuting with h1 inverse gh2. Okay, so the key idea is that the closeness of C and C prime in the hyperbolic metric translates into the boundedness of the heights of these h1 and h2. In other words, in order for x to be close to h1x, it must be the case that h1 has small height. By height, I just mean look at the absolute value of its entries. H1 and h2 here are matrices in SL2Z. So the key is that for them to be close, h1 and h2 are bounded. And then what do I have? Well, I mean, I have, in order for C and C prime to exist, these two CM points that are close to each other, I must be able to find some g commuting with t and with something obtained from t by multiplying by h1 and h2 inverse. So both of these guys I view as linear relations on G. Taking G to be, some matrix over Fp. And now those are linear equations with bounded height. And therefore, for p sufficiently big, a solution exists. I mean, you can show without much difficulty that if a solution exists, it exists uniquely, in which case I can write the unique solution in terms of the of h1 and h2. And so the point is that for p sufficiently large, if such G exists, it can be lifted to an integral matrix with bounded height. Okay, so and then we can conclude that C lies on the corresponding Hecket divisor. So that gives you an idea of how these repulsion results work. It's a little more subtle when I look at the bicusp points, and even more subtle on top of that when I look at the diagonals. But for simplicity, let me just leave it like this. And so now I just need to accomplish part 2. So I need to show that I can bound the incidence of my curve along these special subvarieties in terms of its volume. And this is very much inspired by related work by Huang and To. Let me at least give you an idea of what their results say. So if I take X to be some uniformized complex hyperbolic manifold, so by this I mean it's some compact quotient of a bounded symmetric domain, and I take some totally geodesic complex subvariety. Then these results that they have can sort of roughly be encapsulated by the mantra that if I take the volume of a curve, if I take the volume, the curve spins inside a...
What the curve is 9x. You've got some curve.
So now I take some curve that doesn't lie in Z. So the volume of a curve inside a tube around, a geodesic tube around Z, is bigger than or equal to the volume of a transverse disk times the multiplicity of C along Z. Okay, so they don't have this in this generality. Let me give you sort of two illustrating examples in which they have proven a statement like this. So the first, very simply, is when my subvariety Z is a point. Well, let me call it little z. And so the point is that if Z has a hyperbolic ball of radius r sitting around it in X, then if I look at any curve that goes through Z, maybe it looks like this, the volume that that curve has inside that ball has to be at least as big as the volume of this sort of equatorial disk of radius r, so the volume of the disk of radius r, times the multiplicity at the point. And this bound is optimal in the sense that the curve, which is just m copies of this equatorial disk.
R is small, R is big.
Sorry?
Is this local?
Yes. I mean, it only depends on this ball being embedded in it. Yeah. So the bigger the radius I can take, the more control I have on the multiplicity the curve of a fixed volume has. So the biggest possible r I could take is the injectivity radius. That's why I did that injectivity radius computation, because we're going to use it. Let me give one other example of these Wang-To type results. So for us, this is the only other case we need. And this is when I look in the product of two Riemann surfaces, hyperbolic Riemann surfaces, and suppose Z is some totally geodesic curve lying inside that product. Then the point is that if TR is a tube of radius r,
Let's see these Hector, these special subvarieties are exactly geodesic.
yes, yeah, that's right. So the special subvarieties that give me ramification are one type, but I also need to use the Hecke curves, even though I don't necessarily ramify if I go through a Hecke curve. And we'll see why I need to do that. So suppose I have a tube of radius r embedded around H inside x cross x. So the picture is that I have this totally geodesic curve, and I have some tube of radius r. And once again, if I have some curve C that passes through H, this is H, then the volume it spends inside this tube is at least as big as the volume of the cross-section times the number of intersections. So in other words, the volume of C inside this tube is less than or equal to the volume, again, of the radius r disk times the multiplicity of C along H, in other words, C dot H. Interestingly enough, their proof does not use minimal surfaces, even though a result like this had already been obtained by minimal surface techniques. It uses purely sort of several complex variables that construct some pluri-subharmonic. And I'm running a little bit out of time, so I won't discuss the proof of these results. But let me, in 2 minutes, tell you how we conclude the proof of the theorem, at least in the CM, at least for estimating the CM ramification.
The picture you draw looks very much like all a holomorphic curve is a minimal surface, and so it's going to be a minimal surface.
Oh, it's very much related to the property that the sort of geodesic disks will be the volume minimizing ones. But sort of luckily, at least luckily for me, the proofs don't involve any of that theory. It just involves very sort of just sort of complex geometry techniques. Okay, so just again in 2 minutes to finish. So I need to bound, I want to show that the multiplicity of C along the CM points is little o in the volume. Okay? Well, so now let's look at, let's pretend, let's not think about the symmetric product. Let's just pretend that this is a curve inside xp cross xp. Okay? So my picture of xp cross xp, there are some CM points. And ideally, I would want to put large radius neighborhoods around each of these CM points that are disjoint, that don't intersect each other. And if I could do that, then the multiplicity at each one of these points is bounded in terms of the volume in this ball, and therefore the multiplicity at all of them is bounded by the entire volume of the curve. The problem is I can't do that. I mean, for any radius r, it could be the case, some of the CM points will have a radius r ball around them, but some of them won't. Some of them will be close. But by the repulsion result, the ones that are close lie on a Hecke curve of low degree. Okay, so now the proof is pretty clear. I partition the CM points into those guys that are separated by a ball of radius r from any other point in T, and then the rest of the guys. And the rest of the guys in S all lie on low degree Hecke curves. So the multiplicity, the CM multiplicity, is equal to the sum of the multiplicities. So this first term, these balls I can put by construction in T, I can put balls of radius r that are disjoint around all the points in T. So this is bounded by the total volume of C divided by the volume in a radius r disk. Okay? And the multiplicity along S, again by construction, all the points in S lie on low degree Hecke divisors. So I may as well bound the multiplicity of C along the entire Hecke divisor, HD for d less than m, where the m is the m guaranteed given this choice of r from the repulsion theorem. And now the point is, using the second example, I can bound this. So this is less than or equal to the volume of C divided by the volume of a radius r disk, plus a sum over low degrees of the volume of the curve divided by whatever tube I can fit around HD. Well, the radius of the tube I can fit is exactly the injectivity radius of xp. So now, because we know the injectivity radius is growing, this guy dies in P. And because I can take r as big as I want, again, because the injectivity radius is growing, that shows that this whole thing goes to 0. Sorry, the coefficient of the volume goes to 0. Yes, in other words, it's little o of the volume. And that completes the proof of the claim. Now let me just say that, so this is sort of the easiest case, these CM points. It gets much hairier when dealing with the cusps and dealing with the diagonals. But actually, just using these CM arguments, you can already go home and do the Shimura curve case, because in the Shimura curve case, all you have is CM points. There are no cusps. And so this is already enough to get the theorem in that case.